Hi, this is 4.6 related rates. This is actually going to be one of our quickest videos, but it's strangely one of the hardest topics in calculus is related rates. So we're going to talk about what a related rate is, and then how to find solutions for related rate equations and problems. If we were asked how does the area of a circle change with respect to time, which kind of units there would be like maybe inches squared per second or something like that, compared to how does the radius of a circle change with respect to time. We could look at it with these two equations. We have area equals area of a circle is pi r squared. Okay. Well, if we were to take the derivative with respect to time to both sides, so we'd have to use implicit differentiation, it would be dA dt equals, leave the pi alone, derivative of 2r is 2r, excuse me, that's the derivative of r squared, excuse me, is 2r, but you've got to keep that pi in there. And then again with implicit, then you have to go dr over dt. So that's how we would set up an equation that would help us be able to find out, like for example, if we knew the radius was, or if we were asked if we know that there's 5 inches squared per second, that's how the area of a circle is changing. And we wanted to know, well, how fast is the radius changing when you hit a radius of 10 inches. You could just plug in and solve. It would be 5 equals 2 pi r, and we are looking for, or sorry, r is 10. And then we're looking for how fast is the radius changing. So that's 20 pi, divide that over 5 over 20 is 1 over 4 pi equals dr over dt. So that would be in inches per second. So that's just a quick little example of how you would be asked to solve for a situation like this. What we want to look at is, when we are looking at related rate problems, some strategies. So write all these down. They're pretty good to be able to help you solve related rate problems. So number one, you need to understand the problem. Read it carefully. If it were me, I would highlight all the important information, and then I'd box in the answers that it's looking for so I knew exactly what I needed to answer the problem with. Second step would be to develop a mathematical model. In other words, draw a picture, label the parts, try to be able to distinguish what variables are changing, what do you know, that kind of thing. Third, write an equation relating the variables whose rate of change you seek with the variable or variables whose rate of change you know. A lot of times this stuff is solved with geometric rules like we just did in area one. We might have area, might have volume, might have triangles. It depends on what we're looking at. Fourth step would be to differentiate both sides of the equation implicitly with respect to time. These are rates of change. Rates of change are usually with respect to time, so we want to differentiate them with respect to time. You just have to watch out with this. Make sure you're using the chain rule when you do this. Derivative of the outside, leave the inside alone, derivative of the inside. Because you're not really taking the derivatives. Usually you're not taking a derivative of t. Usually you're taking it of other things like we did area and radius with respect to t. excuse me, substitute the values in, and then solve for your solution, and then interpret your solution. So does it make sense for the problem? So we're going to do two examples. The first example says air is being pumped into a balloon at, so this is where I'm going to start underlining, at a rate of 5 centimeters cubed per minute. So that's a volume, that's a rate of a volume of a balloon. Okay, it doesn't say this on here, but we're going to assume the balloon to be spherical. It should say that, so this is a spherical balloon. Okay, determine the rate. Determine the rate at which the radius, so determine the rate at which the radius of the balloon is increasing. So determine the rate of the radius when the diameter of the balloon is 20. So diameter of the balloon is 20 centimeters. If we go through our steps, we know we need to, number one, understand the problem. So we know there's a balloon, alright, its volume is being changed. The balloon is a spherical balloon, so it's making a sphere. We're trying to find out if there's a constant rate that's being pumped in, or a constant volume changing. That we know we can try to set up an equation to find out how the radius of the balloon is changing with respect to time when the diameter of the balloon is at 20 centimeters. So we need to find out what is the equation of a sphere. So I know that volume is equal to 4/3 pi r cubed. So that's the volume. Excuse me. And I'm trying to find out when we have the volume changing, so V prime is equal to 4/3 times, if we take the derivative of this, we get 3 times pi r squared, and then it's dr dt, which I guess if I'm going to write it that way, I should probably write this as dv dt instead of just v prime. Okay, so there's my two equations that I needed to set up. Now, what do I know and what do I not know? I don't really... I'm trying to find out what is the radius, right? So I know how the volume is changing, right? Or sorry, I don't know or I do know the radius. What I am trying to find is that rate at which the radius of the balloon is increasing. So if I know that, and I know that, then I should be able to plug that in. So let's see. This would be 5 equals, those 3's cancel, so it's just 4 pi times the radius. Well, it says the diameter of the balloon is 20, so the radius is half of that, so that's 10 squared is 100 dr over dt. Okay, so I can solve this to be dr over dt equals 5 over 400 pi, which would be 1 over 80 pi, and this would be in centimeters per minute. Okay, so the volume, if the volume is changing at a rate of 5 centimeters cubed per minute, then the radius is changing at 1 over 80 pi centimeters per minute when the diameter of the balloon is 20. Now, if you think about that, just because the volume is increasing, you can almost think of it when you first start blowing up a balloon, it blows up really, really fast at first. But then it slows down and slows down and slows down as it gets bigger and bigger. So you can tell when we get up to this size with this balloon, excuse me, the volume is still changing at that constant rate, but the radius has really slowed down to that's just 1 over 80 pi centimeters per minute. Okay, I'm going to have you guys try this next one. So go ahead and hit pause, read the problem, and try to solve it using related rates. I didn't go through the steps, but if you go through those steps that I gave you before, it might really help you solve this problem. Okay, so a 15-foot ladder is resting against a wall. So if I draw a wall here, right, the bottom is initially 10 feet away. So if it's a 15-foot ladder, that's 15, that's 10. This is a right angle. We're assuming it's a right angle. Let's just assume it's a flat ground. It didn't really say that, but we're going to make that assumption because it's a math/physics problem. And is being pushed towards the wall. So it's going this direction at 1/4 of a foot per second. So a quarter foot or 3 inches per second. How fast is the top of the ladder going to move up the wall 12 seconds after we start pushing? So I'm going to make this a negative 1/4 because it's going to the left, feet per second. Now this is a really good example that you need your signs to be correct for this to work. So then we're trying to find a positive. It's going to be a positive answer that we should get as far as how this is changing as this goes up the wall, because we're going to assume this is up. So we need to know, how do these things relate to each other? Well, if we call this y and this side is x, we know we have x squared plus y squared equals 15 squared, or that's the same thing as 225. So x squared plus y squared equals 225. And if we wanted to find how these would change compared to each other, we would look at this and go, okay, that, take the derivative of that, you get 2x x prime plus 2y y prime equals 0. Okay, and what do we know in this? Well, we know that the change in x, or x prime, is negative 1/4 foot per second. We're looking for how fast is the top of the ladder moving, so that's the y prime. We're trying to solve for that. So we have that. We have an x. We don't have a y yet, but we could solve this for y. So I can think of this, maybe if I think of it as a 3, I wonder if this could be a 3, 4, 5 triangle. 10 times, no, I don't think it's going to work out that nicely, darn it. Excuse me, but I can solve for y by putting in Pythagoreans and solving. So y equals the square root of 225 minus 100, or y is the square root of 125. So I can use that for y, and I can now just plug it in and solve. So 2 times 10 times negative 1/4 plus 2 times the square root of 125. We're trying to find that y prime equals 0. So if I move that over, I'd actually add it over to this side because it's a negative. So let's see, that would be 20 over 4, which is 5. So then I divide by 2 times root 125. I would get 5 over 2 root 125, which equals 0.2 about, excuse me, and this is linear still, so feet per second. Now notice, because we did this correctly, making that 1/4 negative in that negative direction, you can see that it did work out and give us a positive number because it is going up at 0.22 feet per second. As I look at my answer, I go, well, darn it, that's where the ladder was 10 feet away. This is asking us how fast is the top of the ladder moving up the wall 12 seconds after we start pushing. So we need to find out if this is moving at 1/4 foot away. Let's see, 12 times 1/4 is 3. So really, I need to change my drawing. So I'm gonna take us to a new slide and go, okay. After 12 seconds, this is no longer a distance of 10, it's a distance of 7 feet at the bottom. So that's going to change my answer. So sorry about that, but we got to change this. 2x x prime plus 2y times y prime equals 0. So my x is 7, I need to find my y, so I do y equals the square root of 225 minus 7 squared is 49, which is the square root of 176. So that's my y. So now I can have everything I need to be able to solve for y prime. How is it changing this? I'm trying to find this value again. So 2 times x is 7. X prime is still negative 1/4 plus 2 times the square root of 176 times y prime, which is what we're looking for. And that's equal to 0. So now y prime equals, if I just plug all that in, those 2's would end up canceling. I would get a 7 over 4 root 176, which equals 0.13, and this was in feet per second. So you can see it's going to be moving slower when we get over closer to the wall. The upper part of the ladder is going to start moving at a slower rate than it was when it was 10 feet. Oh, excuse my God. So I hope this kind of makes a little bit of sense. Really work on drawing those pictures, taking the derivative in terms of t, using implicit differentiation. Try to figure out what do you know versus what do you not know. Hopefully you can get it to one equation with one unknown and then be able to solve it that way. So kind of a short video, but I don't think you guys mind that. I think you will need a lot of practice this, so we'll probably spend a good day or two doing this. So bring any questions you have, and we'll see you at school. Thanks.